Dear students, in the previous class we were discussing the criteria for non-uniformity or non-uniform continuity of a function. That is, a function f from a to r is said to be non-uniformly continuous if modulus of x minus u less than delta for all x comma u following a, then modulus of f of x minus f of u greater than or equals epsilon. In this class, let us discuss a very important result regarding the uniform continuity. That is, we already know that uniform continuity always implies continuity. In previous class, we were discussing this result. Uniform continuity implies continuity. But the reverse illusion need not be true. Continuity need not be implies uniform continuity. So we verify this result by using some example. But now we examine whether continuity of a function implies uniform continuity. So the theorem states that's a very important theorem, uniform continuity theorem. The uniform continuity theorem, the theorem states that let I be a closed and a bounded interval. I be a closed and a bounded interval. Then a function f from I to r, a continuous function f from I to r is a continuous function, then f is uniformly continuous. Then f is uniformly continuous. So this is the theorem. Uniform continuity theorem says that if I be a closed and bounded interval, f from I to r be a continuous function, then f is uniformly continuous. More precisely, the continuity on a closed bounded interval should implies uniform continuity. Come to this argument. Continuity in normal case, continuity need not be implies uniform continuity. But the continuity which is defined on a closed and bounded interval, then that continuity is also a uniform continuity. That is the statement of this theorem. So how to prove this one? Proof is by using combination method. Let f from I to r, I be a closed and bounded interval. Let I is closed and bounded interval. F from I to r is continuous. I to r is continuous. Now we assume f is not uniformly continuous. F is not uniformly continuous. So this is our assumption. Since f is not uniformly continuous, we know that there exist some sequences xn, yn. Since f is not uniformly continuous, then by the criteria of non-uniform continuity, by the criteria of non-uniform continuity, there exist the sequences xn and un which presents in I with such that modulus of f of xn minus f of un greater than or equals epsilon with the limit xn minus un equals 0. So this is the non-uniform criteria. So criteria for non-uniform continuity. Since we assume f is not uniformly continuous, then by the criteria of non-uniform continuity, there exist the sequences un and un, xn and un in I with the modulus of f of xn minus f of un greater than or equals epsilon with limit xn minus un equals 0 for all epsilon is strictly positive. Now, listen. Come to the condition limit xn minus un equals 0. Limit of xn minus un equals 0 means that implies there exists some delta positive such that modulus of xn minus un strictly less than some delta. Put delta equals 1 million. Put delta equals 1 by n. Then what do you get? Modulus of xn minus un strictly less than 1 by n for all n greater than or equals a particular stage k. K is positive. Okay. Now listen, what is the secant xn? Xn for an I. Okay, but what is I? I is bounded. I is bounded interval means secant xn is bounded. Xn is bounded. So by Bolzano-Weierstrass theorem, secant xn has a convergent subsequence. Secant xn has a convergent subsequence. Let your xn k be a subsequence of xn. So secant xn k converges. Why? Because by Bolzano-Weierstrass theorem. Okay. So secant xn k be a convergent subsequence of xn. That means limit sequence or limit xn k equals z. Limit xn k exists, let it be z. Okay, secant xn k is converges. Then we assume convergence means limit xn k exists, let it be z. What about this z? Is it lies in I? Sure. Why? Because I is closed. Means it consists of all of its limit points. Then clearly set for in I. Clear? Okay. Now, what about the modulus of unk, what is xnk? Subsequence of xn. Hence, in the similar way, unk be a subsequence of unk be a subsequence of un. What is modulus of unk minus h? Modulus of unk minus h is modulus of unk minus xnk less than or equals plus modulus of xnk minus h by triangular inequality. Modulus of unk minus h equals modulus of unk minus xnk plus xnk minus h. You can introduce minus xnk and plus xnk. Then by triangular inequality, it is less than or equals modulus of unk minus xnk plus modulus of xnk minus h. Okay. But what is un? Limit xn minus un tends to 0. Since unk and xnk are the subsequences of this one, so modulus of unk minus xnk tends to 0, as well as limit xnk equals h. Therefore, modulus of xnk minus h also converges to 0. That means modulus of unk minus h converges to 0. Modulus of unk minus h converges to 0 means modulus of unk minus h converges to 0 means what I get? Yes, it is converges to 0 means limit unk equals z. That is what I. So this again unk presents in I is closed, hence limit point of unk also for an I means z for an I. So limit unk equals z. Okay. Now, but what is f? F is continuous. F from I to R is continuous. This is our statement. F from I to R is continuous. Means f is continuous on I. F is continuous on I means f is continuous at z. Why? Because z for an I. So that implies f of unk converges. Since unk converges to z, f of unk converges to f z. Since f is continuous, so f of un and also limit unk equals z means because as unk converges to z, and f is continuous on I, z represents in I, so f of unk converges to f of z. Similarly, f of unk converges to f of z. Similarly, f of also we know that f of xnk converges to f of z. Why? Because again f is continuous. Also, more limit xnk equals z. Okay. Now, what about the modulus of f of xnk minus f of unk? Now consider modulus of f of xnk, modulus of f of xnk minus f of unk. What is it? which is less than or equals modulus of f of x and k minus h, which is equals modulus of f of x and k, modulus of f of x and k minus h plus h minus f of u and k. Okay. Then again by using triangle inequality, what do you get? Which is less than or equals modulus of f of x and k minus modulus of f of x and k minus h plus modulus of f of u and k minus h. But f of u and k converges to f of h. So it is less tends to 0. F of u and k also converges to f of h. So it also tends to 0. So means it tends to 0. Means which is less than or tends to 0 means it is less than some epsilon. A contradiction to the assumption. We know that yes, modulus of, come on, since f is, we assume that f is not uniformly continuous. So by criteria we have modulus of f of u and k or f of u n minus f of x n greater than some epsilon. So a contradiction. This contradiction is due to our wrong assumption. Therefore, f is uniformly continuous. Okay, so the theorem is very important. That is, that continuity on a closed and bounded interval should always imply uniform continuity. That is the importance of this theorem. We already wrote that the uniform continuity should imply continuity, and its reverse inclusion may not be true, but that if the continuity is defined on closed and bounded interval, that is the very important, that's a crucial point. If the continuity is defined on closed and bounded interval, then that continuity should imply uniform continuity. Okay. Now let us define another, what is that? Which is Lipschitz condition. Lipschitz condition. What is the Lipschitz condition? Let A is a part of it. Then f, define f from A to 1. Then the function f is said to be a Lipschitz function. F is a Lipschitz function if f is said to be a Lipschitz function if there exists a constant k greater than 0 such that modulus of f of x minus f of u less than or equals k into modulus of x minus c. If any function f satisfies this condition, that function is said to be a Lipschitz function, and if the k, here k is said to be the Lipschitz constant. K is said to be Lipschitz constant. Let A is a part of R. If we define a function f from A to 1, then the function f is said to be a Lipschitz function. If there exists any constant k such that k greater than 0 such that modulus of f of x minus f of u less than or equals k into modulus of x minus u. K is said to be Lipschitz constant. If any function satisfies this condition, the function is said to be a Lipschitz function. Okay. For example, what about f of x equals x square? Consider the function f of x equals x square, which is defined on closed interval 0b. X of order closed interval 0b. Find the Lipschitz, f a Lipschitz function. If so, find the Lipschitz constant. How? Means, for this example, f of x equals x square. So what about modulus of f of x minus f of u equals modulus of x square minus u square? Clear? Modulus of x square minus u square means it equals modulus of x minus u into modulus of x plus u, or modulus of x plus u into x minus u. So one step is skipping, so it is modulus of x minus u into x plus u. But we know modulus of x plus u less than or equals mod x plus mod u. Okay, where x fallen where 0. X comma u also fallen close interval 0. That means x less than or equals b and also u less than or equals b. Sure. Why? Because this x and u are vice in close interval 0 b, so they are always less than or equals its upper range. So mod x less than or equals b, mod u less than or equals b, so it is less than or equals to b. Clear? So here supply it is less than or equals to b into modulus of x minus u. So that means modulus of f of x minus f of u less than or equals 2b into modulus of x minus u. So the k equals 2b, hence f is a Lipschitz function with the Lipschitz constants. K equals 2b. Agree? Suppose f of x equals 2x, that's immediate. When f of x equals 2x, consider f of x equals 2x, where x is fallen close interval 0. So what do you get? Here what about modulus of f of x minus another example. Modulus of f of x minus f of u equals modulus of 2x minus 2u less than, equals 2 into modulus of x minus u. So here 2 be the Lipschitz constants. Agree? So now a function, if it satisfies Lipschitz condition, then it should be uniformly continuous. If a function f from a to r, then if a function that a is a part of r, f is defined from f from a to r. If f is a Lipschitz function, then f is uniformly continuous. If a function satisfies Lipschitz condition, then it should be a uniform continuum. Uniform continuity, if a function is uniformly continuous, what about the reverse solution? It may not be satisfies Lipschitz condition. So that is proved in later. So here, how to prove this one? So proof is immediate. Suppose f satisfies Lipschitz condition. Means if f is a Lipschitz function, then there exists a constant k, Lipschitz constant k greater than 0, such that modulus of f of x minus f of u strictly less than it is less than or equals k into modulus of x minus u. Okay, k into modulus of x minus u. Put up delta equals some epsilon by k. Delta is a positive quantity, k is positive, epsilon is positive, so delta equals epsilon by k. Okay. If modulus of x minus u less than delta, therefore this become modulus of f of x minus f of u strictly less than k into, since the strict inequality hold, why? Because of modulus of x minus u is delta, k into delta. Okay, that equals k into, what is delta? Epsilon by k. Epsilon by k equals epsilon. That means if modulus of x minus u less than delta, then modulus of f of x minus f of u strictly less than epsilon. That means f is uniformly continuous. Okay? Yes. If f is a Lipschitz function with a Lipschitz constant k, then we have modulus of f of x minus f of u less than or equals k into modulus of x minus u. If modulus of x minus u less than delta and delta is already arriving as some epsilon by k, then modulus of f of x minus f of u strictly less than epsilon by using these arguments. That is nothing but the condition of uniformly continuity. So, if a function is Lipschitz, then it is a uniform continuous function. What about the reverse solution? If a function is uniformly continuous, then it need not be a Lipschitz function. That is, it need not be a Lipschitz function. So, listen. For now consider f of x equals f of x equals root x, where x is falling closed interval 1 infinity, or f of x equals root x where x is falling closed interval 0. So what is the modulus of f of x minus f of u? Modulus of f of x minus f of u, which is equals root x minus modulus of root x minus root u. Clear? Okay. Which is equals modulus of root x minus root u into modulus of root x plus root u divided by modulus of root x plus root u. Clear? On numerator it is modulus of x minus u divided by root x plus root u. Clear? That means modulus of f of x minus f of u, modulus of f of x minus f of u is modulus of f of x minus f of u equals modulus of x minus u into modulus of x minus u by root x plus root u. That is, it is less than or equals 1 by 2 into modulus of x minus u. 1 by 2 into modulus of x minus u. Why? Because x is falling closed interval 0 and closed interval 0 2. So it is root x less than or equals 1, and when root u less than or equals 1, so it is less than or equals half into x minus u. If modulus of x minus u less than 2 epsilon, so what it is? Modulus of f of x minus f of u less than or equals 1 by 2 into strictly less than 1 by 2 into 2 epsilon equals epsilon. Therefore, f is uniformly continuous. Okay. But f of x equals root x. What is f of 0? 0. So what about the modulus of f of x minus f of 0 equals f of x? Modulus of f of x minus f of 0 equals modulus of f of x. Means there does not exist a k greater than 0 such that modulus of f of x less than or equals k into root x, or k into mod x. Modulus of f of x, here modulus of f of x, so there does not exist k greater than 0 such that modulus of f of x less than or equals k mod x, means f is not a Lipschitz function. So the reverse inclusion